Let's wait for 10 more seconds. After that, we will start the session. Okay, let's start the session. So, welcome to the sixth tutorial session of Operation and Planning of Power Distribution System, whose instructor is Professor Sanjeev Ganguly sir from IIT Guwahati. And I'm Satya Vikram, a PMRF research scholar here in Department of Energy Science and Engineering, IIT Bombay. So in this, we will see the reliability part. Yeah, in the previous tutorial session, we have seen the few of the performance matrices like SAFI, DAFI, and there were various different types of indicators were there. So in this, we will go through the reliability basics and then build on the some numerical parts that will help you to solve the current assignment. Okay. So without wasting time, let's move further. So here the first problem on your screen. So this is the basically first question and this is the second question. Okay. First try to solve the first problem, then move to the second part. Okay. We will see the basics, and if you know the definition, just let me know in the chat box, or we will see okay, what is the correct answer is there, and we will give the description of that. Try to solve. If you know the answer, just write in the chat box. Try to solve the first problem. This is just a straightforward equation is given in the reliability and failure rate. Okay, let me give the solution for the first problem. So, there are two terminologies here given. Uh, First is like reliability, which is denoted by R, and the second is the failure. Failure is denoted by F. Okay. So basically, when you see, suppose there is a system is there, okay, and it have to perform a certain action, and they have to give them some output, okay. And in this system, if we try to add the disturbance, suppose I try to introduce some disturbance, okay, and system is able to perform this output with some tolerance band, like suppose this is the intended operation that output should be maximum here and output will be minimum here, okay, and certain disturbance came and then output was in between of this value, so we can say that this is a reliable system is there. Okay. Okay. So one second. Okay. So if it performs the intended operation, so it will say that the system is robust and system is reliable. Okay, even if having the disturbance, so system will perform the intended operation and it is able to achieve the objective. Okay, so if you see the time frame, suppose this is a time t. time t, capital T, all overall time t. So suppose I take a timestamp here t. Okay, this is the time t. Okay, so at this point of time, if you're having a certain reason, or you can say that the system is something behaving like this, okay, and it was there in the band, so we can say that it is. You can say that below this the system is reliable, or after that it is after disturbance. This is the time frame in between it got disturbed and then again come back into the okay. So these are the means theoretically stating that this is the intended operation with respect to time. Okay. So basic definition, the failure rate, basically how to define that. The failure rate is being defined. So here you also have the failure of a component. Okay. So the failure of a component at a time particular t is equal to probability time less than or equal to t. Okay. So it means that if we give the time frame that in the 0.3 second system should come into the their intended operation case, and it should perform that work which is being assigned. Okay. So if in the point 0.3 second it is not able to come back, so we can say that in point 0.3 time frame how the failure was there. Okay. If t is less than or equal to t is there, so we can call it as a failure. Okay. If it is a we can say the system is above to come, so we can say that reliability is equal to 1 minus ft, that is basically equal to 1 minus p times of t less than equal to t. Okay. So from here also you can see that if t represent the failure time of a component, then the ft represent so the instantaneous failure rate at a time t. Okay, ft is the failure basically. Okay, let me explain by taking a new slide. So just wait for few seconds. Okay, so suppose there is a component is there. Okay, and there is a kind of initial phases will be there. So means reliability of the system, so reliability will be constant or sub timer, and after that it try to reduce. Okay, and then if you do the some repairing or something, then again it try to come back and try to perform the intended operation till life t. So suppose I consider this is the time span t of this component. So so below this failure reliable system. So yeah, the after the repairing, because the reliability is also having a one component as a repair also, that we will see the matrices MTTB or MTTBF. So that kind of reliability matrix we will see. Okay. So here also the instantaneous failure rate at a time t. Okay. Let's move forward, try to solve this. This also I have already explained, but try to solve and give the answer of the second part. So this was the first and this was the second. Okay. Okay. So I got one answer at option C. That is true. That we have already seen that FT is the failure rate, and which is equal to probability time uh, t, which is less than equal to basically time t, where it is given here t capital less than equal to t. Okay, and the reliability is basically probability of time greater than t, reliability, sorry. So when you see that both are actually complementary. Okay, so we can say that rt reliability is equal to 1 minus ft. Okay, so option C is correct. And also when you see what is the f5, actually to try to solve this second problem, it is a quite interesting. I wanted to explain few concept in here. Here you have to explain that what is the meaning of f5 is equal to zero point 0.3. Any answers? Okay, let me explain. So f5 is if you compare with the equation, this ft equation. So what is depicted basically? Let me take another color. So f basically ft is equal to probability of t less than or equal to t. Okay, so which is given as zero point 0.3 and t is here the 5. So you can say that time is actually 5 units because the units are not given whether it is a second, hour or anything. So you can say that 5 units. And what is zero point 0.3? 0.3 is basically probability. Okay, so the failure rate will be 30% at time overall spent time is less than or equal to t. It means that suppose there is a lifespan of a component is there, okay, and at a initial time frame which we have given that ki this time will be there. So below that time frame the 30% probability is there the failure will occur in that particular component. Okay, and survival rate, what is the reliable rate? It is actually 60%. Okay, that you can say in given time frame t, the if you go in that time frame, so reliability is basically 60%, that is 1 minus ft, and failure rate is actually 30%. Okay, so that what it depicts. Okay, so here some mathematical concept which is already given in the presentation slides from the professor. So just I wanted to few give the some glimpse. So here if you see the time to failure random variable t has a density function ft. So you can say that this is a function of failure rate. So reliability is 1 minus ft. So you can say that what is the overall duration of the ft? Ft basically capital Ft. So you can say suppose this I consider the function ft. Okay. So in this time frame, suppose this is a 0 and this is the t1. So this was the some kind of curve is there. So you can say that ft, that is the failure rate, is basically it's a density of this. Density of this means area. Okay, you can say this is the area in between. So that is also called as a ft basically. So you can plot the ft with respect to t. Ft is basically a density function. So when you take the area out of that in between 0 to t, you can say that this is a equation of the ft. But when you subtract by 1, it is gives the area in bit from the this t to infinity what was there. Okay, so this is called as a reliability. So you can say that failure rate is basically 0 to t ft dt, and you can say the reliability of t is equal to t to infinity ft dt. Okay, and if you wanted to find out the what is the probability of failure in between the two time stamps, suppose this is a time t1, this is a time t2, and some kind of this failure function is there, probability density function of the failure is there ft. So you can say that in between t1 and t2 you just have to t1 and t2 f2 you can write it like this f0 to t ft or 0 to t f t1 ft, or you can say that like this t1 to t2 ft dt, okay, is equal to t1 to 0 ft dt plus 0 to or you can say the 0 to t2 ft dt. Just you have to, here you have to take the reverse. So means ki you have to 0 to t1, so you can just negative of that. So you can say that 0 to t2 ft dt minus 0 to t1 ft dt. So that is called as the ft2 minus ft1. Similarly, when you see that ki if you wanted to find out the reliability out of that from this in between that this time stamp, okay, you just have to, what you have to do, reliability is 1 minus ft2. You consider r t2 minus 1 minus r of t1. Okay, when you find it out, it will come out to be r t1 minus r of t2. Okay, so this is basically the when you wanted to find out a failure rate in between the time stamp t1 to t2. Okay, let's move forward, try to solve this problem. So this is a kind of a one hazard rate is one terminology is there. So you have to find out what is actually the hazard rate in between the time t1 and t2. If you already know, just give me the answer. If you don't know, I will explain that. Okay. Okay, I got option B. Okay, let's wait for 2 minutes, and after that I will give the solution. Just this option we just verify whether it is correct or not. Just read the statement what is given. Okay. Okay, let me give the solution. So in this problem, basically the option D is correct basically. So hazard rate, that HT is actually defined as minus 1 upon RT, okay, dRT by dt. That I will explain in the further question, that how it actually comes. So basically, when you see the first statement, the probability that a component fails exactly at time t2. Okay, so this is not a hazard rate. Okay, this is a hazard rate from which, so Here it is asking the rate. Rate is already, it is some kind of slope behavior will be there. Okay. Or when you see that there is a kind of rate of change of uh, velocity. Suppose I am taking, okay, so this is acceleration. Okay, so this is a kind of rate. When it is given, it means that something dv by dt or something v2 minus v1 divided by t2 minus t2 term will be there. Okay, so the first statement is exactly false because it is telling that probability that a component fails exactly at a time 2 t2. So this is not a rate, this is probability. Okay. Second, it is saying the probability that a failure occurs in the interval t1 t2 divided by total population. No, because if you see the probability in between the t1 and t2, that is not a rate. So it means that that is a density basically. So when you have a particular density, means probability with respect to time, that is called a density basically. Okay, that is false. Third, you can see the conditional probability per unit time. Conditional probability per unit time that occurs. No. So this is not a probability basically. Hazard rate is basically reliability function slope. Okay. Let's take example out of that. Okay. Mhm. Suppose this example, the question is there. Okay. So it is there. It is telling that R 100. So this is kind of time interval at a 100 time the probability is reliability is 0.92. Okay, and at a 1/20th second the probability was 0.85. Okay, from this the point, suppose I wanted to plot this. Okay, at this 100. Okay, so suppose this is reliability, so you can say this come out to be 0.92. Okay, at 120 it was dropped to 0.85. Okay, so uh, 0.85. Okay, suppose I wanted to ask that key whether this with the time, with respect to time, whether the reliability is increasing or decreasing. Okay, so if the reliability, how to quantify that, how to quantify it? Suppose this slope, when you see the slope, so this is kind of decreasing slope is there, so negative slope is there. Okay, negative slope means it's basically showing that it is decreasing. Okay, so that is a kind of hazard rate. Suppose it is kind of it was something like this, so you can say the hazard is actually increasing, and if it is decreasing, you can say the hazard rate is actually decreasing with the negative slope. Okay, so this is a when you have the reliability at a particular time stamp, so using this rate you can quantify that how much rate is actually going to be there in the two time stamps. Okay, so the equation is something like this. Ht is basically equal to rt1 minus rt2 divided by minus basically rt1 t1 minus t2, or you can say that if you take the negative inside it will become t2 minus t2 basically. Okay, so this is similar to like this now, r1 upon rt drt by dt. Okay, so this is a basically the hazard rate. So when you put the values in this, suppose this is st basically, rt1 means r at a 100 time, that is 0.92 minus 0.85 divided by t2 minus t1, that is come out to be 20, and rt1 is basically 0.92. when you solve it, it will come out to be 0.0038. Okay, so the till the time, what we have learned, what is the reliability? Reliability is basically function of t greater than t. So this is reliability basically equal to probability time t greater than t, and has what is the failure rate? Failure rate is basically probability t less than or equal to t, and we also know that ft is equal to 1 upon rt, 1 minus rt basically. And then we have seen the hazard equation, that is st is equal to rt2 minus rt1 minus rt2 divided by t2 minus t1 rt1. Okay, let's move forward. In the similar line, in the hazard rate problem itself, there is a one reliability function is given, that is rt is equal to e to the power minus 0.004 t square. So you have to determine the what is the instantaneous Hajar rate St at a time t is equal to 10 units. Okay, try to solve this. Use the similar equation which I have given previously. Any answer? So let me give the solution. Okay. So what we have seen, listen here. So what we have seen that what is the hazard rate equation St is equal to St is basically 1 upon RT dRT by dt. No, okay. Let RT is already given. No? RT is given e to the power minus 0.004 t square. Okay. Let's try to find out what is the dRT by dt. When you solve, it will come out to be minus 0.004 2t e to the power minus 0.004 t square. Okay. So when you see this equation, it is basically minus 0.008 t, and this is basically the RT only, no? So this is basically RT. So this is RT. Okay. Then put this equation into this ST equation. So ST is basically equal to 1 upon minus 1 upon RT multiplied by minus 0.008 t RT. Okay. When you try to solve this RT will get cancelled out. Okay, and the HT equation will come out to be minus plus basically 0.008 t. So what is he asking? H10. Okay, put the value 0.008 multiplied by 10, it will come out to be 0.08. Okay, per time, per unit time. Okay, so this is basically you try to solve like this. Okay, so the st is equal to minus 1 upon rt drt by dt. So rt equation is e to the power minus 0.004 t square. Drt we have solved and then fitted the value here like this, and then put if the time is equal to 10, we able to find out what is the instantaneous hazard rate at t is equal to 10 units. Okay, so the answer come out to be option B. Okay, so you just have to remember the equation. The st is equal to minus 1 upon rt drt by dt. Suppose you find it out what is the hazard rate of r1. Okay, you just have to put the value 1 upon r1t dr1 by dt. Okay, you can find it out like this. Okay, so let's move forward. So it will come out to be so it will come out to 0.08. Okay, try to solve this. So there is a equation of also the probability that component survives in beyond 5. So this is a probability problem that I can clarify in the further discussion. So if you know the answer, just try to solve, and after that I will give the answer directly. Okay. Okay, I think nobody is able. So I didn't got any answer. Okay, so let me explain. So what is actually it is saying? So when you see, it is saying that a component has a constant hazard rate, which is constant. That is, a lambda is basically 0.002 failures per hour. Okay, so it means that the in a hour the 0.002 failure will occur. Okay, so the probability to component the survive beyond t is equal to greater than 500 hours. Okay, so there is a one equation is there, finding out the probability, reliability basically. So the component survive. Okay, so the it formula is e to the power minus lambda t. Okay, so let me explain what is says basically. Okay, so this is when you solve the equations which is already provided in the lecture slides. There you can see, find out this formula. Okay, so which says that the probability that the component survives beyond the 500 hours. Okay, so if you say the what is the reliability equation was there, reliability at a time t is equal to probability that time is less than t. Okay, or you can say the what is the failure rate. Failure rate is basically probability of, sorry, here it will be greater than, so it will be greater than t, and this is a time less than equal to t. Okay, what is asking, it is asking beyond 500. Beyond 500 you use the probability of reliability basically. So this is expressed in the Poisson distribution form, that is a e to the power minus lambda t. And you can say that what will be the probability e to the power minus lambda t. You can put the value, lambda is basically given already 0.002, and the time is also given the 500 hours. Okay, when you try to solve, it will come out to be 0.3679. Okay, so the option B will be the correct. Okay, so overall crux of this problem is that you have to just remember that the reliability, when the failure rate is given, or you can say the failure hazard rate is given, which is constant. Here you should remember that this is a constant hazard rate. Okay, when there is a constant hazard rate is given and it is asking that reliability, or indirectly you can say what is saying, probability that the component survives. This is also can be one statement. Okay, so in this, the reliability, when you find out, it will come out to e to the power minus lambda t. Lambda is already given, you just have to find out at a 500 hours, so it will be e to the power minus 0.002 multiplied by 500. Okay, so this will come out to be 0.3679. Okay, let's move forward, try to solve this. I will explain what is the this terminologies are the mttf, mttb, and mtt r, what is there. So I will explain that. Just if you know the answer, just try to solve. Okay, I got one and two answers there. Option C. Okay. Let's see what is correct basically. So here I wanted to explain few terminology: mean time to failure, mean time to repair, mean time between failure. Okay. So suppose there is a component is there. Suppose let's take the example of charging station. Okay. EV charging station basically. Okay. So EV charging station will be such that, so this will be some EV charger will be there. Okay. So this is the EV charger, and there are guns will be there, and this is the one EV will be there. Okay. So what is the operation? Important part is that this charger should charge the EV. Okay. So sometimes what happens that this charger is not able to supply the power to this EV. Okay. So in the situation when it comes that EV charger is not able to charge the EV, so this is called as failure of the charger. Okay. So you can say that the situation came that ki EV charge, what is the important point from the charger point of view, that ki it should charge the EV. If it not able to charge, whatever the reason is there, if it not able to perform the intended operation, so it is called as failure. Okay. So this is called as a failure of charger. Okay. Then what happens? We repaired the charger. Okay. So this failure of the charger came at the time t1. Okay. So at time t2, which is greater than the t1, then we repaired the charger, and then it able to perform the operation. Okay. Then again, after time 13 time t3, it again got failed. Whatever the reason was, then we again repaired at t4, and then it started to operate. Okay. So when you see in the plots, at time t1 failure came. Okay. And at time t2 we repaired. Okay. At time t3 failure came, and again at time t4 we repaired. Okay. So when you see this operation when you see first failure, this is the first failure, and this is the second failure. Okay. So in the sequence when you see, so there can be possibility that there will be third failure, fourth failure, fifth failure, time frames will be there. Okay. So when you take this time t3 minus t1, t3 minus t1, so this was the difference of time between the failure. Okay. And when you take the multiple failures, and then you can see the fifth failure came, means okay, third failure came. So this was basically, suppose this is t5, so this was a t5 minus t1. So when you take the average time of that, so average means this was some time, this was time by 2. So this is called as the mean time to failure. Okay. This you can see that mean time to failure. Okay. So this was basically the at the first time when the failure came, and after that when it got repaired, and then after that the failure again came. So this is the time bit difference between the failures, and when you take the average, so this is called as the basically the failures, basically mean time to failure. Okay. The mean time to repair when you see, so this is the time frame in between this t3 minus t2. Okay. So when you see the t3 minus t2, and again t4, then t5 failure came, the t6 time got repaired. So when you take the difference of repair timing, so when the repairing was got started, and then the second failure second sorry, this will be till t4, so this will be t4 minus t2. Okay. So mean time to, no, 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 that is fine. T4 minus T2, when the repair got started, and there were multiple repair times were there. Okay. So it was performing the intended operation at certain time frame, and then again it got certain failure, and then it got repaired, and then again performing. So when you see that uh, multiple failures comes. First failure came at some time t1, then it got repaired, and then again got failure. So this kind of architecture you always see in the most of the components. Okay, so when you take the time of failure 1, time of failure 2, time of failure 3, this is basically the time frame delta t, you can say. So divided by n, means ki plus dot 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 t f n. Okay, so this is called as the failure time, mean time to failure. So when you take the mean time to repair, basically the time taken to repair the item plus time taken to repair the item 2 in the second time frame plus dot 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 till n, and then divide by n. Okay, mean time to between failure means when the first failure came and the second failure came, what was the time frame? Okay, Be- before the means ki when you say the repair happened and then second fault came into the system, then you can say the what are the time frames are there. So major crux is that you just have to remember the terminology. Statement will be already given in the questions when it will be asked, then you can solve accordingly. Okay, so here in this problem, when you see what it is saying that what lambda is given, that is constant failure rate is given, and is asking what is the MTTF. So this is basically the 1 upon T. Basically MTTF is basically 1 upon lambda. Okay, this is the one formula. You just have to remember. So you remember that what is the reliability? Reliability is basically e to power minus lambda t. Just remember what is the mean time to failure, which is equal to 1 upon lambda. This is just to integrate. When you integrate 0 to infinity, you will get this value. Okay. So when you integrate 0 to infinity e to the power minus lambda t dt, it will come out to be 1 upon minus lambda e to the power minus lambda t 0 to infinity, 0 to infinity, it will come out to be 1 upon lambda. Okay, so that is called as a mean time to failure. Okay, and when you say mean time to repair, this is basically 1 upon 1 minus lambda. Okay, when the failure came and the repairing happened, that is subtracted. Okay, so answer will come out to be 2000. Okay, that is correct. Remembered? So you got the what is the field of what is the MTTF, what is the MTTR, what is the MTVF. Okay, and just remember this formula 1 upon lambda. Let's move forward. Try to solve this. So in this problem, it is saying for a component with a constant failure rate lambda, expected life is given by like this. So which of the statement, four statements are given, which is options are actually correct? Just let me know. Okay, option B, I got option B. So option C also here. Okay. Oh, let's wait for 10-20 more seconds. After that, I will give you a solution. Okay, option C. Okay, let me give the solution. So actually, the option C is correct. Why I am saying that? So we have already seen what is the reliability equation is there. Reliability equation, you know, e to the power minus lambda t, and the expected life ET is equal to 0 to infinity RT dt. Okay, when you solve it 0 to infinity e to the power minus lambda t dt, that we have already seen in the previous question, when you solve it, it will come out to be 1 upon lambda. So the lambda is actually constant failure rate, And then this expected life, what is came is the reciprocal. So expected life is actually the reciprocal of the constant failure rate. So option C is correct. So which option I got? The option B, which is actually the I'm not expected life. This is basically the reliability. Okay. So this is exponential with the time, decreasing exponential, basically uh, like this. So this is a kind of reliability. Okay, reliability decreases with the time of the component, age of the component. Okay, initially the reliability will be high, and with the time the reliability will decrease. Okay, let's move forward and try to solve this. In a non-repairable system, when the system cannot be repaired, with a constant failure rate lambda is given, which statement is actually correct? Try to solve this. Okay, I got multiple answers at option A. Okay, so that is already correct. No, we already have seen mean time to failure. So correct. So here the multiple options are correct. So option A is already correct. We already know, and it's a non-repairable system. Okay, so it means that the you can say also the MTTF increases as the failure rate increases. So that is false because it's a decreases as the failure rate increases. So option B is false. Is the expected value of time to failure? That is also true. Okay. So when you see the hazard, the constant failure rate, that is lambda. So lambda is basically the constant failure rate whose unit is basically the failures per unit time. Okay, so here it is saying what is the MTTF. MTTF is basically 1 upon lambda. Lambda is basically, here you can say the failure time. Okay, so expected value of time to failure. So when you see that next failure when it come out to be, it's a kind of expected value, it's an average. And also through the means description also you can say what is the MTTF, mean time to failure. Okay, so or you can say that expected time to failure. Okay, MTTO applies only to repairable system, that is false. You can apply to the non-repairable systems as well. Okay, so let's move forward. Try to solve. So here the two statements are correct, the A and C. Okay, try to solve this. Okay. Okay. A, B, I got one answer. Also C also. Okay. Uh, okay. Let me give the solution. Okay. A, B, D. Okay. Let's see whether it is correct or not. Okay. So the correct option is A, B, D. Okay. So A is the correct by definition that we already know. Ki MTBF mean time to failure is equal to MTTF plus MTTR. Okay. So mean time to failure and mean time to repair. Okay. When you sum it up, it will come out to be MTBF. Okay. Second option B is correct. E is defined as a mean cycle time, operating time, and the repair time. That through this also you can judge that option B is correct. Okay. So when you see the option D is correct, MTBF is a downtime due to the repair through R. Okay, so MTBF is a 1 by lambda always. So this, sorry, D. C is false because MTTF is equal to 1 upon lambda. Okay, not in a kind of when the repair time is included, that is false. MTBF is basically equal to repair time M plus R. Okay, mean repair time also it will be considered. Option D, when you see, is correct because it is including the repair time. Okay, includes repair time because MTBF. Okay, that actually the sum of mean time to failure and mean time to repair. So it will, when the first statement is correct, so it is already including the repair time and the failure time. And the B, when you see it, a mean cycle time, that is also true. It's a mean value. And option D, when you see MTBF, it is actually including the repair time, so that is also correct. So when you see the MTBF is 1 upon lambda always, that is false. Okay, because when you see here in the equation, MTBF is equal to MTTR plus MTTF, mean time to failure. Okay, and mean time to failure, what we have seen, it's a non-repairable system, that is 1 upon lambda, or generalized also constant hazard rate is there, a constant failure rate is there, 1 upon lambda. So when the mean time to repair is 0, it can, you can say that it will be mean time to between failure is 1 upon lambda. But this is not the always the correct. Okay, so when this will be the only the condition when the MTTR is 0. Okay, that's why the option C is actually correct. This is not, if it is said ki generally, or you can say that not always. Okay, so then the option C can be correct. Okay, getting my point. So just remember the MTBF is include the both the failure and the also the repair, and it can be 1 upon lambda, not always. Okay, and it's a mean value and it includes the both the repair and the failure. Okay, let's move forward, try to solve this. Mu is basically the mean. Okay, mean, or you can say the lambda also, that is also correct. Okay, I got one answer, option A. Check whether the multiple options can be correct. Okay, option A, B, C, I got one more answer. Okay, okay. So I got the A, B, C, three answers at A, B, C. Okay, let's check. Let's check. Okay, so that's true. That A, B, C is actually good. This is good sense that you are getting the points. Okay, you're just relating the concept and getting the correct answer. Okay, that is correct. That MTTR is the reciprocal of the mean repair time. Mu is the repair time basically. That is being defined. Not mu is the repair time, basically the inverse of that. B is correct because the changing mu changes 1 upon mu. So it changes the MTTR. So in the it is saying the MTTR depend upon repair time. That is true because it's a, if you're changing the mu, then the inverse will be also changed. Then it will also be there. Okay. So when you say the option C, MTTR affect MTBF, that is true because we have already seen MTBF is equal to MTTR plus MTTF. Okay. So D option is MTTR is independent of maintenance policy. That is false. It depend upon the maintenance policy how you are going to repair that system, how effectively, after how much time. So maintenance policy is important criteria to see what will be the MTBF. Okay, MTTF and MTTR. Okay, so that's also option D is incorrect. So option A, B, C incorrect. Try to solve this. Okay, I got answers A, B, D. Check again whether it is correct or not. Okay, ABD is second answer. Re-verify whether it is correct or not. Looks like all. Okay. Let's see. Let's see whether it is correct or not. So in this statement, when you see, it is saying when the failure rate increases, the repair and while the repair time is constant. So it is saying repair time is actually constant and failure rate increases. So, so when you see through this, we don't know any definition, we don't know anything. Okay, just layman terms. If the repair time is constant and the failure rates are actually increasing, suppose this was the time T1 when the first fault came. Okay, and this is the time T2 till the time it got repaired. Means T2 minus T1 time it got repaired. Okay, then again it got a failure rate occur. Then T3 then again it got failed. Then the time then again it got repaired and so on. Okay, so when you see the failure rate which was increasing, basically failure rate is actually increasing and the repair time is constant. Okay, so mean time to failure decreases. When you see the first statement, mean time to failure decreases. So, that is also can be corrected. Okay, when you see that mean time to failure is actually decreasing. So the time frame. So when the failure is occurring at a faster rate, so the mean time to failure is actually decreases. That's true. Okay. Okay, so the time at which the fault were coming, so mean time actually got decreased because the failure rate is increasing. Okay, mean time to between failure decreases. When you say the mean time between the failure, it is also actually decreasing because the faults are coming at a faster rate. Okay, MTTR changes, that is false because that is already true that here the repair time is actually remain constant. Okay, so if the repair time is constant, it means the average is also constant. Okay, mean is also constant. System ability decreases. That's true. Okay, because when you see the system ability, because the fault is coming at a faster, repair is not happening. So the fault is you can say that a system operation is actually got affected. So in that sense, when you say system ability got decreased because the fault came at a faster rate. Okay, getting my point. So option A, B, D is actually correct. Here also you can say the A, B, D option is correct. Option C is false because the repair rate constant implies mu is constant. You can read it out. Okay. So just through the analogy also, when the repair time is constant and the failure is occurring at a faster rate, so the mean time to failure got decreased and mean time to between failure also decreases. System ability decreases. Okay, let's move forward. Try to solve this problem. I think this is the last problem in between MTTF. Okay, try to solve this. Try to solve. Okay, I got answers B, C, D. Okay. Hmm. So we got answers at B, C, D. A, C, D also at C, D. Anyone else? Okay, without wasting time, let's give the solution. Okay, so the option A and D is actually correct. When you see option A, D, A and D, okay, option A and D is correct. Why? So it is saying कि MTTF is used for non-repairable system. What was the statement? It was saying used for non-repairable system. That's true that it is MTTF is used for the non-repairable system. Okay. So what is option D? Option D is MTBF includes the repair time that we have already seen. That is true. This is true. MTBF is always greater than the MTTF. That is false. Okay. Why? MTBF is equal to MTTR plus MTTF. Okay. So how can you say that ki MTBF is greater than the MTT? Okay. Is always greater than the MTTF. No, not always. It can be equal because if it is a zero, so in this situation the MTBF is equal to MTTF. Okay, so it is not always greater than. It can be greater than equal to. Okay, in that situation this is false. MTBF is equal to MTTR for non-repairable systems. That is true. When the repair is not happening, it will be equal. Okay, equals to MTTF for non-repairable system. So option C is also actually okay. Non-repairable MTBF is generally not the metric unit movement, so you use MTTF. Okay, so that is also correct in the by the definition when you see. So option A is correct, option C is correct, and option D is correct also. Okay, C is also correct because when you see MTBF is equal to MTTF for the non-repairable system when the repair is not happening. That's true. Okay, I will correct that and give you the solution. Okay, try to solve this. So try to solve this. I will wait for 1 minute. After that, I will give the formula. Okay, option C I got. Okay, because this is based on the formula only. If you know that formula, then it will be easy to solve. Okay, so I will give directly the formula, and you will be able to solve. Okay. Okay, I got one answer. Option C. Others. Okay, let me give the directly the formula. Okay. So this is basically the formula that is a T, basically the mean cycle time. So mean cycle time is equal to 1 upon lambda plus 1 upon mu. Okay. What is lambda here? You say the failure rate and repair time. So this is a kind of failure rate. This is the repair time. Okay. So that is a similar kind of uh, you can say description of MTBF. Okay, so MTTF is basically the MTBF is the overall system architecture. So 1 upon lambda, you already know MTTF, and 1 upon mu is the MTTR. Okay, so this is a similar kind of concept. Mean cycle time is equal to 1 MTTF plus MTTR. Okay, so when you try to solve this, it will be 1 upon 0.004 plus 1 upon 0.02. You will get the 300. That is correct. Option C. Let's move further, try to solve this. And I think that is similar kind of problem is there, but one reverse will be there. Okay, try to solve, I will give the solution. Option A. Okay. Okay, option A. So don't waste time on this. So we already know that failure time is basically uh, overall time when you see lambda over lambda 1 upon mu per failure. Okay. So when you see it's a lambda mu divided by mu plus lambda, but it is asking here the failure frequency. Frequency will be equal to lambda mu divided by mu plus lambda. So it will come out to be option A. Okay. So here also it is written frequency is basically lambda mu divided by lambda plus mu. Okay. And when it is asking the time, so time is equal to 1 upon frequency, you can use the lambda plus mu divided by mu lambda. Or you can say 1 upon lambda plus 1 upon mu. Okay. Let's move forward. It is already given. So we will not waste time in the. I have already given the formula here. So ability is basically uh, ability of a two-state model. Okay, so if you're having a two-state, whether is a on, whether is a off. Okay, uh, means there will be no in between system is there. So it either it will be overall available or it will be always unavailable, kind of. Or you can say 1 upon ability is equal to 1 upon 1 plus 1 upon or you can say lambda min me. Okay, so this is the one of the formula when you see or you can directly use this. Okay, so ability formula, if the lambda and mu is already given, just put the formula and you can get the answer. So ability is basically equal to mu divided by lambda plus mu, and repair time, that is overall time frame, was equal to 1 upon lambda plus 1 upon mu. Okay, so it will come out to be zero point 0.9. Okay, let's move forward. uh, this is a very simple problem. I will give you 10-15 seconds to solve, and just just let me know whether it is you are able to solve or not. Very very simple. Let's see. Okay, okay, that's true, because the system is available to the 0.92 time frame, or you can say the percentage or reliable time frame. So the ability unavailability will be the system just is the 1 upon a. So okay, so that is also correct. Okay, let's move forward. So this is a one kind of configurations are given, multiple configuration. Uh, so there is an analogy. Analogy is like this. Let me explain. Suppose there is a parallel system is there. Okay, so suppose the parallel resistances are connected. Okay, and here there is a one voltage source is there. Okay, so if the current is flowing from here I, and suppose the equal resistances are there, so this is I by 3 and I by 3 and I by 3 will be there, and there is a some switches are connected. Suppose I connected one switch here, one switch here, one switch here. Okay, so suppose this is switch 1, switch 2, switch 3. Okay, so in this kind of system, when the switch 1 was on, let me make a table. Okay, S1, S2, S3, current will flow or not. Okay, on or off, kind of. And this is the state. Okay, here. Suppose switch 1 is off and the switch 2 is off, or system switch 1 is on. So current will flow, no? Current will flow. I will flow. Suppose the state is such that this was on. Okay, then also current will flow. And suppose this state is there, then also current will flow. Or you can say when the all is on, then also current will flow. And also when the 2 is on and the 1 is off, then also current will flow. Or you can say this is on, then also current will flow. Or there can be situation that this is off and this is on, 2 is on, then also will flow. There is only one situation when the all the switches is off, and then there is will be the no current will flow. Okay, So in this system, it is saying that there is a three parallel paths are there. At least one component is available. Then your intended operation can be performed. Means current can flow. Okay. This is a kind of parallel representation of reliability is there. Okay. Suppose I take the one situation like this. So this is a current. This is a resistor like this. Okay, and then I have connected one switch here, one switch here, one switch for this. Let me take one switch here, one switch here, one switch here. Okay, now the system will behave something else. Okay, if at least one switch is off, then there will be no current flow. Okay, so to current to flow, all the system will have to operate. It means that in this kind of system, each component is important, and failing of the a single component, the reliability of system will become zero. But that is not case in the parallel system. So with this analogy, let's move forward. Okay. Suppose this is the one. There are various configurations are there. Here it is given. So reliability of each component. Suppose the one component, second component, third, fourth is given. So all the reliabilities are the 0.85. Okay, so you have to find out what is the reliability, what is the equivalent reliability of each configuration. Okay, I'm giving you a few seconds to solve the first part, what you are able to understand. Okay, first and second. After that, I will give you the how to solve the multiple layers and multiple configuration will be there, then how to solve that. Try to solve the first a part first. Let me know. Okay, I got answer at r to the power 4. Okay, let me explain. Okay, let me explain. I will give you the some structural formulation, then you can solve it by yourself. Okay, here when you see, listen here. So when you see the first part, so let's see the first part. Okay, okay. So here when you see the reliability of this component, R the R is the reliability. So suppose the only the two components are there. Suppose this is the two components are there in this. Okay, and the switches are there. Okay, so this reliability of this system operation is depend upon the both the component, or you can say the both the switches. Okay, in this situation, if it's a one system is there, so the reliability was pointed to what is already given 0.85. Okay, but when you have a two system, okay, and the first system operation is also dependent upon the second system operation, so a second component operation, so the reliability will drop down. Are you getting my point? Because the intended operation of the first unit is also dependent upon the second unit. So that's why the when you two system are connected in two component are connected in series, then the reliability will drop down. You cannot drop the reliability by just adding. You can drop the reliability by multiplying. Okay, so this is a kind of operation is there. So it is like this. So this will be the there are individual components are there, no? So there they are the independent components. Okay, so the probability of reliability of a particular first component. Okay, so or you can say like this. Let me explain. So reliability of a system is basically when the first component, suppose 1 2 3 4, probability of operation of the first will be there, probability of the operation of second will be there, third will be there, and the fourth will be there. Okay, so their reliability components is already given 0.85, so you can multiply 0.85 0.85, so it will come out to be 0.85 to the power 4. Okay, but when you see the second system is there, so this is the one part of the component and the second part of component is there. Okay, so their operation, the first operation is when you see this branch, this is already the 0.85 to the power 4, and the second when you see it is 0.85 to the power 4. Okay, but when you see the both the unit reliability, so they are basically the actually if this line, this branch got failed, the second branch will be there in the operation. It means that keeping the two branches, the reliability will increase. How it is going to increase? Let me show you here. So the reliability of the system formula is basically like this: 1 minus r m to the power n. M is basically the number of units connected in parallel, and n is the number of units connected in series. Here in this formula, there is a 1 minus 1 up 1 r will be there. So what we have already seen the formula r, here is the 4 units are connected in series, and the other 2 units are connected in parallel. So here yum is basically the 1 2 3 4. Okay, and there is a two component which are in the parallel fashion. When you see here option B, so in this when you see it will come out to be 1 minus 1 upon r to the power 4 chi square. Okay, so this is a kind of option B. Okay, but when you see the third part, this, okay, so this is a one system, and this overall system is in the series with this. Okay, that's why you have to multiply. Here also when you see here we have multiplied. Getting my point? So multiplication decreases the reliability because the two are in the series, and the same two series are in the series, and that two series systems are in the parallel. You just have to multiply. Okay. When you see this part, option D, this this system, they are in the parallel. So you have to multiply each. So here also when you see here also option D part, here the two systems are there, 1 minus 1 upon r square and 1 minus 1 upon power r cube, because 3 I think it is there in the parallel. So it's option E. Option E answer is this. Okay, and this is the option D. Okay, because when you see this all systems are in the series, option D. So here when you see the all system are series, so you just have to multiply because two components are there in the parallel, and then two components are in the all the parallel series are there. So you just have to multiply 1 minus r of square, multiply again 1 minus 1 upon r of square, kind of to the 4 times. Okay, so then you will get the power 4. Getting my point? You just have to remember this formula, that is 1 minus r to the power m to the power n. And also you can verify with the answers that when the series components are connected, the reliability will drop down, and if the system are connected in parallel, the system reliability will increase. Okay, getting my point? So there is a one problem here I have kept. You have to try to solve this. Okay, just try to solve. This is a very simple problem, and just try to solve the first part. After that, I will give the solution for the BCD. Okay, just try to look the statements and try to solve. This I have taken from the presentation itself. Okay, try to solve this. First part solve. After that, I will give the context of BCD. I will give you one more minute. After that, I will give the solution. Okay, let me give the solution. Okay, so here there is a three-phase transformer is there. Okay, it is actually a three single phase system is there in that. With that, it is created the three-phase transformer. Okay, so the reliability of A is given as 0.90. Okay, or you can say that the success rate of that transformer A. Okay, identified a three single phase identified is okay. And the second transformer is there, which is of a probability of 0.95. RC is actually 0.99. Okay, so what is the probability that all system will perform in the intended operation? Okay, it means that probability that ki A should also perform, probability that B should also perform, probability of C of the also perform. Why? This is basically the when you see the intersection of all three units, because three all three units are independent units. Okay, so when you see probability of A intersection B intersection C, all the systems at a common part, basically this A B C, this part. Okay, so this is basically when there are three independent units are there. So this is basically probability of A, probability of B, probability of C. Okay. So in the option A, what is saying, question A, it is saying the probability of having no failure transformer at a given time. It means that all the are in the success condition. So zero point 0.9 multiplied by 0.95 multiplied by zero point 0.99. Okay, this is the answer. But when you see the second, what is saying that if one of the out of three transformer fails at a time, what is the probability for the unit being the transformer A, B or C? So in this situation, when the probability A fails, okay, suppose the A fails, okay, so A fails, the probability will be equal to what will be the probability in this situation? Probability A in the off state, probability B, and then probability C is there. Okay, A is basically 1 minus 0.90 multiplied by 0.95 multiplied by 0.99. Okay, similarly when you see the probability when the B is failed, so probability of A, probability of B of bar, and probability of C. Okay, so this situation, and in the similar manner when you see the C part, there also you can take the two are not functional, C is functional kind of. Okay, because all the independent units are there. When you see the option fourth statement, what is saying, what is probability of having all three transformer out of service? This means that probability of A not, probability of B not, they are also functional, probability of C not. So it means that it is 0.10, this is 0.0505, and this is the 0.01. You multiply and you will get what is the probability when the all the three are in the out of service. Okay, this is a chart. Okay, that is also giving the sense that given the A intersection B intersection is there, so that is basically independent unit. So probability of A multiplied by probability of B multiplied by probability C. Okay, let's have a few problems related to the basic electrical that will also help you to solve the few questions in that assignment. So these are the basic problem. Four problems are there. You have to just guess and solve. Okay. I will give you one minute to solve that. 1.5 minutes. Okay. Try to solve this. Last 15 seconds. Okay, let me give the solution. So here when you see the problem question IT is given, the current IT, it is equal to I fundamental plus third harmonic component. Okay. When you see here 3 omega term is there, so this is the third harmonic. Okay, and there the unity there, so this is the fundament. Okay, and here also when you see the voltage, it is fundamental. Okay, so always remember that the consumption in the load will be always the fundamental current, and the other harmonic component. Okay, 1730. Okay, let me solve. So other the harmonic component, they will go on the heating. There is not, these are not being utilized. Okay, so it means what is the power formula? Power is basically Vrms, Irms, cos phi. But when you see here in this problem, what is the power consumed by the load? So it will be Irms 1. What is phi? Phi is basically phi V minus phi I. Okay, let's put the values. Vrms 230 root 2 is given. So this is the amplitude, that is the maximum. What is the RMS? RMS is basically 230 root 2 divided by root 2 is equal to 230. Similarly, what is the IRMS 1? So it is equal to 8. Because when you divide by root 2, it will come out to be. What is the cos? What is the cos theta V? Theta V is basically 0. What is the theta I? Because both are in the sign, so you can directly add and subtract. What is minus I? Minus 20 degree. So it will come out to be plus 20. Okay. So this is basically 230 multiplied by 8 multiplied by cos 20. Okay, it will come out to be 1729 watt. Okay, 230 multiplied by 8 multiplied by cos 20. Okay, so it will come out to be 1729. Okay, always remember that all the harmonic component will go into losses, heating losses. Fundamental will be utilized or consumed inside of the load. Okay, try to solve this, but to find the total RMS value in this. You can tell in the under root also. Just write the SQ and answer. Okay, 8.06 amps. Okay, just wait for 10-15 more seconds. After that, I will give the solution. Okay, let me give the solution. Uh, so the total RMS current will be when it is given in the, this is the DC component, this is the fundamental, this is the fifth harmonic. Okay, approximate times. Okay, let me solve. Fifth harmonic. Okay, so when you have the DC component also plus fundamental also plus other harmonics are also there, so there is a formula that you just have to use IDC square plus I1 of square by 2 plus I2 square by 2 plus dot 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 whatever the nth component harmonic will be there. Okay, here when you see what is the IDC, IDC is 5, 5 of square plus what is the I1, I1 is basically, I1 means I1 amplitude, amplitude, amplitude means maximum value. Okay, so it will come out to be 6 root 2 of square by 2 plus here when you see 2 root 2 of square by 2 plus dot dot dot. Okay, So what it will come out to be, because the second component is already 0. Okay, so it is 0, and then we have taken the first DC, then fundamental, then fifth. It will come out to be 25 plus 36 plus 4, 40 and root 85, 30, 40, 65, sorry. So it will nearly across 8 times. Okay, that is correct. Okay, let's move forward. 562. That's correct. That's correct. 562. Okay. Let's move forward. And this was 8.06. Let's move forward. Try to solve this. Let me make the architecture. It will make you easy. So the source is given. You have a ZS here, and then you have a ZL here. This is the VS. So you just have to find out the what is the RMS voltage across the load. What is the voltage here? VL. Vs minus Zs is equal to VL. No, this is not correct. Okay, that is true that ki Vs minus VL will be equal to voltage across this, but not the impedance. 155. Okay, let me give the solution. Okay, so you just have to use the voltage division principle here. Voltage division principle. So what is the voltage across the L is equal to simply Vs ZL divided by ZL plus Zs. Vs is already given 230. ZL is already given, that is 6 minus J2. Divide what is the ZL plus Zs when you add 9 plus J2. It is asking in magnitude. Magnitude means 230. Here it will be 36 plus 4, 39. 9 9 81 plus 4, 85. So it will come out to be nearly, when you solve, I don't know the answer, but it will come out to be 157.7 nearly. Okay, here I have solved with the voltage. Okay, finding out the current, but you can solve with the voltage division also. That is also fine. Okay, let's move further with the last problem of this session. Just try to find out this. Okay, cos 25, that is 0.906. Okay, that is correct. Okay, what we can say here, that is false. So the solution is not correct. So here when you see the voltage is already given here, the 230 root 2, and the fundamental it is there sine omega t, that I am taking the sine. The current is already given, that is the fundamental 10 root 2 sine omega t plus 6 root 2 sine 5 omega t is given. Okay, and also it is given the phase angle between the voltage and current is 25 degree. So this I can consider minus 25 degree. Okay, so the total power factor is derived with respect to the fundamental only. Okay, so it will come out to be cos 25 degree, that will be equal to 0.906. Okay, we are not taking here the power factor of the fundamental component, which is not being utilized. Okay, so if it is asking the total power, then we can compute with this 5 omega t, but here also you have to give here the fifth harmonic component of the voltage. Okay, which is not there, so power will be the zero of the fifth harmonic component. Okay, that's all for the today's session. So we have seen few of the problem related to probability. Okay, 0.75. Okay, let's verify, Raghav, in the further that when I will upload the slide, try to find it out. We will discuss in the next tutorial session. Okay. Okay, that will help. This tutorial session will help you to solve the current assignment, and I will upload the slide by today only. Okay, that's all for today, and thank you so much for joining. Okay.